Okay, so homework 2B is due a week from today. Do I remember correctly that you submitted homework 2A?
Yeah.
And homework 1? I've provided comments on homework 1. Ironically, I've never seen the student view of what it looks like from your perspective when you get your grades. I know it's different from the instructor view, but I typed in a little response to each of you. So just as a test to see if you can see the instructor remarks, please go into your grade book and see what I wrote. Because the homework grader that is going to be scoring your work this semester, his intention is to occasionally use the little sticky post-it notes right there on the PDF that you supply, but more of the time I think his approach will be to type up a summary of maybe the points you missed or what the issue is in that little comment area. So that's going to be your only chance to get feedback on the homework. Unless you come to my office. If you've got questions, I always welcome you to stop by my office. Like if you have a concern with the way your work was graded, ultimately I'm responsible, although I delegate that responsibility to the homework grader for the homework assignments you turn in. If you have a problem with the way something's been graded, please don't just fester and stew and let it bother you. Come see me, and I'll try and make sure that it's right. So anyways, homework 1 is graded already. Homework 2, I'm going to give the grader the solution manual, and he'll start working on it soon. Homework 2B, a week from today. No lab this week if you're in the Civil Engineering 319 lab. So no lab this week. We'll get back to our normal schedule next Wednesday. Any questions before we start talking about pressure and surface tension? Is there any left? Send it back around. Let's do another round, guys. Another round of shots. All right. For the record, we're not eating shots in the class. It's candy. We're eating candy. Okay. Hopefully this one's not screwed up. Okay, so the pressure that's being measured is, it's using the Earth's atmosphere as 0. Like if you use this pressure gauge and your tire's completely empty, and you put the pressure gauge on the valve stem and nothing comes out, it's going to say 0 as the beginning point. But it's not actually 0. You know, the air that we're breathing, there's something there. It's just that in the case of, thank you. Yeah, I think that's probably about right. If you just eat the little peanut fragments, there's no calories there. If it's just the little bits. Yep. All right, so the point is that datum is another way to say the basis for measurements. And so our pressure datum, when we're measuring the pressure of a tire, is Earth's atmosphere. So we're saying, let the atmosphere be 0. But a tire in outer space has a different datum. Like if we were going to put a pressure gauge on that tire, now instead of on the other side of the on the other side of the wall of this tire. On one side is the compressed air, on the other side is Earth's atmosphere in this picture. In this picture, on the inside is pressurized air, although I don't actually know. Maybe they were tubeless tires that were solid. I think it was probably air in there to save on weight. On the outside is no atmosphere. And so this would be an absolute pressure measurement, whereas this is a gauge pressure measurement. That's what we call it when we're measuring relative to Earth's atmosphere. We call it a gauge pressure. So absolute pressure is using a vacuum as 0, whereas like my tires in Huntington, if I was going to measure the pressure in my tires, it would be atmospheric plus the actual pressure inside the tire that's over and above atmospheric. So if I keep my tires at, I don't know, what did I assume here, 34 psi, then the absolute pressure is going to be the relative pressure plus the atmospheric. And so in terms of kPa, we say that the typical atmospheric pressure in Huntington is probably about 101 kilopascals. And then the pressure in my tires above that is 234 kilopascals. And so then the total absolute pressure in my tires would be 335. Now gauge pressure is using some other reference point as where we begin our measurements. And so atmospheric is our measuring point. So in Huntington, the gauge pressure is 0 of the atmosphere. That's measuring how much the atmospheric pressure is relative to itself. So it's 101 kilopascals minus 101 kilopascals. And so the gauge pressure of the atmosphere in Huntington is 0. And therefore my tires would just be whatever the differential is that little stick gauge says. This little stick gauge already has built in the assumption that you're starting with atmospheric pressure as your 0 point. So here's an illustration that shows that in different way. The vacuum pressure is absolute 0, and on Earth the typical sea level pressure is 101 kilopascals, and so the atmosphere is above that by a certain amount, 101 kPa. Now, my tires are more pressurized than the Earth's atmosphere, but I can measure it. I can measure the pressure of my tires either all the way back to the vacuum, which was the true 0 point, or I can measure how much pressure there is by just going back to the atmospheric. So you can see the gauge pressure is 234, but the absolute pressure is that 234 plus how much difference there is between vacuum and atmosphere. So do you remember from our last class on Thursday, when do we usually use absolute temperature? Because we talked about difference between relative and absolute in terms of temperature in class on Thursday. It's gases, right. So whenever you're working with gases, you'd use absolute temperature. And in the same way, oftentimes when you're doing gas law type problems, you'll also have to use absolute pressures in a lot of cases. So here is a gas law example. I apologize that we had to rush through the example, gas law example number 1 in class on Thursday. Let's take a little bit more time for this one though. It uses that same formula that density is the pressure of the gas divided by the R for the gas and the temperature. So here we have a 2.5 cubic meter tank of oxygen. We're going to pressurize it to 7,650 kilopascals, and that's an absolute pressure. The tank, the steel of the tank is 50 kilograms, and then the temperature of the whole system is 120 degrees Celsius. So what's the total weight, taking into account not only the tank, but also the gas? And I think to be more precise, I'm asking what is the mass, not just what is the weight. what is the mass? Let me update that slide to say that. What is the total mass? All right, so let me pause the recording for a minute, give you some time to calculate based on the volume. You're going to need to know the density of the gas. And then once you have the density and you know the volume, calculate the mass of the gas. All right, so the pressure is force per area, so newtons per meter squared. So my point about units is that if you write 7,650,000 newtons per meter squared, then including the units is going to help you to see when you do and when you don't need to expand something out to be dimensionally consistent. So the R value, 259.8 joules per kilogram Kelvin. Now the joules we could expand out ultimately into kilograms, meters, and seconds, but we won't go through that derivation. We just, in this case, know that it's going to cancel out to where the density is going to give us kilograms per cubic meter eventually. And then the temperature will be 393.13 Kelvin. So when we do that, the density of the gas should be 74.90 kilograms per cubic meter. Did anybody else get that same 74.90 kilograms? Oh, no. That's better. I expanded out the units here just for the curious. A joule per kilogram Kelvin is the same thing as a meter squared per second squared Kelvin. And we see if we put that full expression into the density, when you cancel out the units that are in both the numerator and the denominator, cancel out the Kelvin, and of course a Newton is a kilogram meter per second squared. We do get units of density for the density of oxygen, and then the mass of oxygen that's there is going to be the density times the volume. So there will be 187.24 kilograms of oxygen inside of that canister, which has a mass of 50 kilograms. That's the mass of the steel of the cylinder. So the overall mass is 273. Oh, it looks like maybe I did want the weight after all. I was intending the weight, so I meant what I said. When we have the mass, we find the weight by then just multiplying it by G, and then it'll tell you the number of newtons. So let me change that back again. The materials have a mass of 50 kilograms, and what is the total weight? I'll put it in bold so I don't forget that that's what I really mean. All right, so I can leave this solution up another minute if you want to take a look, or if there's anything you want to ask about here in this one. So it's a gas law problem where we're using the gas law constant R for a specific gas, not just the universal one. We know the molecular weight of this gas, so we have the R value specific to oxygen. We know the temperature in absolute terms. We've got the pressure in absolute terms. So from that all, we were able to calculate the mass and therefore the weight. Any questions on this example? So pressure is a unit of force over some area. And it's not just a fluid property, it's a solid property as well. Right now, maybe you're feeling pressure on the bottom of your feet because you have a a certain force related to maybe the weight of your leg, acting downward through the area, the foot area that you have. The reason why they wear snowshoes in the winter to walk on top of snow is that the snow can only bear a certain force per unit area, and so by spreading out the human body's weight over a larger area, it doesn't exceed the capacity of the snow. So units of force per area, pressure. We'll do a lot more with pressure, but let's turn our attention to a property known as surface tension. Okay, this picture here, what's happening and why is it possible? So what's going on here? Who wants to take a crack at diagnosing the image we're looking at? All right, so it's bug on water. How do you know it's water and not plastic? Yeah, you can kind of see a little deflection in whatever this is. It's water. You know, there are bugs that have specifically adapted to environments like this so that they can walk on the surface of the water. And so there's some property there that enables a bug to walk on water. So, you know, what are the specific reasons why this is possible? Well, first of all, if this bug was really heavy, it wouldn't work. So it's partly possible because the bug doesn't weigh a lot. And we also notice it has some certain length. Its leg length is part of the key here. If its legs were shorter, it wouldn't be able to do it either. If we think from a force balance perspective, you know, the downward forces of the weight of the bug are resisted by something. And what that resistance is the surface tension. So the surface tension is that the molecules in this water are attracted to each other so much that their bond with each other at the surface is greater than the downward force of the bug. And there are similar variations of this experiment where you can have even a paper clip float on water. And what's notable about a paper clip is that we know that the paper clip's made out of steel. And steel has a higher density than water, and so it shouldn't float. Not from the standpoint of density, but it will float on top of the water because the attraction that water has for itself, those polar bonds, are very strong, especially at the surface. So in just a minute I'll show you why it is at the surface those bonds are even more attracted, but let's, just because it's fun, let's watch this video clip of a video of bug walking on water. Surface tension and why it allows things that are heavier than water to float on top. The forces at the top of a water-air interface are greater than underneath because consider that the water is attracted to all of the molecules surrounding it. It has a certain amount of molecular attraction, but this one that's in the middle, it has attractions with the one to either side, the one beneath, and also the one on top. So think it's just got a certain number of bonds, and it's spreading out those bonds across 4 different molecules. Now we're just thinking in a single dimension. In reality, since it's 3-dimensional, there's one in front of it and one behind it. But for our purposes of our illustration, it's fine just to think in 2 dimensions here. Now the molecule at the top, it's attracted to the one on the sides and also the one beneath. But since there's no molecule above it, that same bonding force is expressed over fewer molecules. And so the attraction at the top is higher than for the water molecules beneath because there's no water molecules above it. So at the surface, there's a greater attraction, and we call it a tension, than for the water molecules beneath. And we can look up in fluid property tables what is the surface tension of different liquids. For water, you can see that surface tension is a function of temperature. And as the temperature of water increases, the surface tension goes down. And so those water molecules are more weakly bonded as the water heats up. Usually we're going to use a surface tension constant of 0.073 because that represents the temperature of room temperature water. But there are some liquids that have a very high surface tension constant. Remember mercury, the liquid that has a really high density? It also has an extraordinarily high surface tension. And that's why one of its interesting properties of mercury is that if you have some of it and pour it on a table, it'll form kind of a mound. It won't spread out in the same way that most liquids do. It'll pile up, even though it's a liquid. It's a pity that it's toxic because it's so fun to play with. I remember when I was in elementary school, they let us play with mercury. So, yeah, not great. That surface tension at the top creates a membrane effect, and the way that you can calculate the magnitude of that surface tension force is it's the surface tension constant multiplied by some length. Now, we should have had a clue that this was going to be the formula if you look at the units of surface tension. The units of surface tension constant, sigma, is newtons per meter. So it says if you have some length parameter there, multiply the surface tension constant, sigma, by a length parameter, and that'll tell you the magnitude of the force. So then the only question is, like, what's the length in question? The length over which the surface tension acts. Now, let me give you a hint going back to the bugs. Remember, part of the reason why it has long legs is to spread out its force over a longer area of the water. Well, that fits in nicely with the equation we just saw, because what we know, if we do a force balance, there's the weight of the bug acting downward, and then the surface tension force is pushing up. So let's just consider a cross section of this leg. The leg is probably circular if we draw a cross section, and what it's doing is it's bending the water, and it's doing it in two spots. It's doing it on the left and on the right. And so actually, if we were going to say maybe this bug has a leg length of a centimeter. So this bug has 4 legs, well, maybe more. Those ones up front aren't as long. But what you'd need to do is you need to add up the total physical length of the bug's leg, and then you double it, because what it's doing is it's bending the water on either side. So just to clarify, the force due to surface tension is that sigma, the surface tension constant, multiplied by length. Length isn't always just a physical dimension. You also have to take into account how is that physical thing interacting with the water. And in the case of the bug, there's twice as much interaction length as there is physical length of the bug's leg. Does everybody get that point? Yeah.
Is this the same or different as like a buoyancy force from displaced water?
Great question. This is different. Sometimes there will be both a buoyant force and a surface tension force, but this is different. That's a really good question. I'm glad you asked that. We'll get into buoyancy a little bit later. All right, so there's something called the capillary effect, and we're going to observe it in the lab, where if you have a small diameter tube, if it's made out of glass in particular, if you dip the tube down into water, what happens is the water gets drawn up into the capillary tube. And the smaller the diameter of that tube is, the higher the water goes. If you have a really, really fine tube with an extremely small diameter, then the capillary draw can be quite high. And the reason for that is that the liquid molecules are attracted to the glass wall. Glass is, the main molecule in glass is silicon dioxide, which is polar, just like water is polar. And so what the water is trying to do as it's drawn up inside the capillary tube is maximizing the contact area with the outside of that glass tube. But we can do a force balance on a capillary tube like this by considering the tube diameter. And in the case of water, there's a contact angle that is essentially very close to zero. In other liquids like alcohols or oils or mercuries, there may be a more distinct contact angle where, this meniscus, where the water kind of climbs up the edge even a little bit more, would be more pronounced in some of those other liquids. So the surface tension force in this case can be calculated by the surface tension constant, and then pi d is the relevant length parameter for a circular glass tube. We already talked about the bug legs and how you'd calculate the length parameter there. It would be the double of the physical length of the legs that are down in the water. But here, this is circular, and so the circumference of the water around the outside edge that's in contact with that glass, so pi d, is what we'd be using. And the cosine theta is thrown in there just in case we're working with a liquid that isn't water, because the surface tension forces are straight up because of the zero contact angle for water. But in some other liquids, the forces may only be partially up, and some of the force would be in a different direction. So we'd have to account for the angle if it's a liquid other than water. So what about this? What if we wanted to know how high the water is going to be drawn upward? So what is delta H? How can we find delta H? Well, to do that, we do a force balance. So we want to know, let's just work an example so we can see the specifics of it. If we have water at room temperature and we have a surface tension constant of 0.073 newtons per meter, how high is the water going to rise if we know the inside diameter is 1.6 millimeters and a water temperature of 20 degrees Celsius? So the key here is to do a force balance. Okay, let me work this on the screen on the whiteboard, and I'm going to pull it up on the screen so that it's on the recording as well. All right, so first of all, it told us the temperature of the water. And if the water temperature is specified, what that means is that you need to get the specific fluid properties for that temperature out of the back of the book. And at 20 degrees Celsius, the unit weight of water is 9790 newtons per meter cubed. That's a little bit lower than the typical 9810 newtons per meter cubed that we'd use as the default assumption for the specific weight of water if the temperature wasn't provided. But since it is, we'll look that up. Also, the surface tension constant for water at 20 degrees is 0.073 newtons per meter at 20 Celsius. Now what we're doing is a force balance where we've got the water and a tube went down into the water, and what happened is the water is going to rise to a certain level. And so the force balance is going to be the weight of the water acting downward is going to be balanced out by these surface tension forces. Now, the surface tension force, there's not two of them. There's just one. It's working all the way around the outside edge, and it's pulling up. So I'm going to write the force due to surface tension and indicate it as an upward force. And so if we're going to do the force due to the surface tension is up minus the weight of the water is down is equal to 0 because it's in equilibrium. So remember, what we're trying to find out is how high does the water rise? What is delta H? That's the unknown, is the height that it's going to rise to. Now, first of all, the formula that we saw for the surface tension, the force due to surface tension is sigma times some length parameter. What about the weight of the water? What can we know as the formula for the weight of the water? What we're talking about, by the way, is it's the weight of the water that's above the water line. So it's not all the way down to the bottom of the tube. It's just how much higher did the water go in the tube than it should be if there was no surface tension pulling it up. So what's going to be the formula of the weight of the water inside that cylindrical glass tube?
Volume times density.
Good. Volume times density. So volume times density. That would give us the mass. Then we'd also have to multiply that by g to get the weight. So instead of volume times density, let's do volume times specific weight. Because if we use specific weight, then it will give us the weight of it rather than the mass of the water. Okay, so first of all, the surface tension force is going to be sigma, the constant, pi times d, and cosine of the angle. Since it's water, the cosine of the angle is going to be 1. So I'm not even going to bother writing that. It's just going to be, well, maybe I will, cosine of 0 degrees, which is 1. Okay, minus the weight of the water. So the weight is going to be the circumference times the height, right? So the volume is going to be delta H for the height, and then, oh, not the circumference, it's the cross-sectional area, pi d squared divided by 4. Because I was confusing, we don't want the outside area, we want the actual volume of that cylinder. So the volume of the cylinder will be the cross-sectional area of the top. So remember, there's some diameter. And in the problem statement, it told us that this is the diameter of the tube is 1.6 millimeters. 1.6 millimeters, which is 1.6 times 10 to the minus third meters. So that is this diameter. .6 millimeters diameter. Okay, so this is our surface tension force. Here is our weight. So we've got the volume, and then we also need to multiply it by the specific weight of the water, gamma. So, and then we set that equal to 0. So that's volume times specific weight, and that'll give us units of newtons. Okay, so I've got it set up. What I'd like you to do, plug in the numbers and try and solve what is the delta H. How high is that going to go? Delta H is how many millimeters is the water going to be drawn up inside of this glass tube because of the surface tension of wanting to maximize that contact with the glass. They really do need to expand the line of stuff, right? 5-hour energy, peanut butter sandwiches. All right, who got 18.6 millimeters? Good, 18.6 millimeters. Let me put it up on the screen, and then we'll talk about what that means. Come on. Almost there. All right, so you rearrange the equation, if you like, to solve for delta H. And we get 0.0186 meters, which if you multiply that by 1,000 is 18.6 millimeters. By the way, on a quiz or an exam, if I say express the answers in millimeters, then I'd have to give you a small, no matter how minor, there would be some small deduction if if you only left it in some other units. But what happens if we make the diameter smaller, the diameter of the tube smaller? What's going to happen to delta H? It's going to go up. So this one was 1.6 millimeters. What would happen if we took that diameter in half? What would happen to the delta H if instead of 1.6 millimeters, what if we made the diameter of the glass tube 0.8 millimeters? What would having the diameter do to the delta H? Good. Why quadruple? You're exactly right. Right, because it's diameter squared. So if you make the diameter half as large, then the cross-sectional area is 1/4. So you're reducing the cross-sectional area. You're also reducing the force, but you're reducing the cross-sectional area more. Okay, so let's take a look at one other slide. This is a slide that I'm going to show you again in another class lecture, but just to cap things off, what we've been talking about today, both pressure and surface tension. The full description of pressure is pressure intensity. And the reason for that is that pressure is a scalar, meaning that it doesn't have direction, it only has magnitude. And it's acting equally in all directions. Here's a little trick question. What if we had these two reservoirs? Oh, I shouldn't have told you it was a trick question. I blew it. All right, we've got two reservoirs. One of them is a really big one, and the other reservoir is more narrow. Which one has a higher pressure at the bottom?
They're the same depth, it's the same pressure.
Exactly right. If it's the same depth, it's the same pressure. We'll talk about why that is, but when I was younger, it always seemed so strange to me that sometimes people would do like, excuse me, scuba diving tests in really narrow ponds that would go very deep. It just seemed like somehow the pressures would be different, but they're not. Pressure doesn't depend on the width of the fluid, it depends on the depth of the fluid. And we'll get into the hydrostatic equation later. But the idea of pressure is that it acts equally in all directions. And so if you're down at the bottom of a swimming pool and your ears hurt, you can't turn your head to avoid that pressure. It's not like sticking your head into the wind or turning away from a loud sound. The pressure is acting in all directions equally. Okay, so that's all I have for you today. Let's take one last look at these announcements before we finish. Remember that your second homework assignment, you can get an early start on that now. We'll go over a couple of the key ideas in class on Thursday, but that assignment is due on Tuesday of next week before class, and we don't have any lab section this week. So I'll see you on Thursday.